So how are we going to be using these things? So we're going to be using dy to approximate function values. In practically speaking, for problems, we want to think of dy as a new function on its own. It's the product of the derivative and this change in x. In practically speaking, this is what we're going to be using from here on out. So now let's look at an example. Find the differential dy for this function, e to the x over 10, when x is 1 and dx is 0.1. So if you remember the definition for the differential dy, we need the derivative of f and dx. We're going to take that product. So we find the derivative of f of x, and we find that the differential dy is e to the x over 10 times dx. So now we evaluate dy when x is 1 and dx is 0.1, and I get this value of 0.01 basically. This was the entire value from Desmos, but practically speaking it's 0.01. And so what this is telling me is for this function e to the x over 10, near x equals 1, when the x value changes by 1/10, this is what the function value changes by. So now let's look at another example. So compute delta y and dy for this function when x is 3 and dx is 0.8. So first let's compute dy. So remember that's the product of the derivative of f with dx. So we find the derivative. I multiply that derivative by 0.8 and I evaluate it at x equals 3 to get 0.4. So the differential dy is giving me an estimate for the change in this function when I go from 3 to 3.8. So now let's look at the actual change. That's delta y. That's the actual change in the function, as opposed to dy, which is just the approximate change based on the tangent line. So if I figure f of x plus delta x minus f of x, that's the change in the function value. And so x plus delta x is 3.8. F of x is just f of 3. So I get the square root of 1.8 minus the square root of 1. And I get an approximation of 0.3416. So delta y is the actual change in the function value. And you can see here, now my tangent line is this blue dashed line, and the graph of the square root function is the red graph. And delta y is the vertical change on the function, on the graph of the function as I go from 3 to 3.8, whereas dy is the vertical change on the tangent line as I go from 3 to 3.8. So that differential dy is just another way to approximate function values for changes in x. Another example, use differentials to estimate the change in the circumference of a circle when the radius increases from 3 to 3.2 centimeters. So what is our function going to be that we're finding the estimate for? The circumference of a circle. And when the radius, notice that the circumference of a circle is 2 pi r. So it's dependent on the independent variable r, the radius. So we want to know how that changes, that circumference changes when the radius goes from 3 to 3.2. So in other words, there's a change in the radius of 0.2 centimeters, which means that delta r is 0.2. So using differentials, we're going to remember that for my function c equals 2 pi r, dc is the derivative times delta r or dr. So the derivative of this function with respect to r is just 2 pi times 0.2, which is the change in x, which gives me 0.4 pi centimeters. So this is telling me the circumference will change approximately by 0.4 centimeters for a 0.2 centimeter change in the radius. And we can check that by figuring the actual circumference when radius is 3 and the actual circumference when radius is 3.2 and finding that difference. So this was delta y, this was dy.